Our discussion on the Chomsky hierarchy and the different types of computing machinery brings us to the most general automaton of them all, the Turing machine. So a Turing machine is a structure with a control unit and a tape. The control unit decides on the state transitions as well as possible modifications on the tape. And the tape is itself basically a memory unit consisting of cells that can be blank or hosting one symbol among the alphabet that the Turing machine is defined on. The tape is infinite in either direction, and by direction we mean left or right. That is one way of defining this. And as I have just said, it can be modified on the run. When you decide on a state transition, you can not only make the transition, but also overwrite whatever symbol is on the current cell. The tape position is read. The execution starts from the leftmost non-blank position. So you have the let's say data or the input already written on the tape, and the leftmost position is going to be the cell that is going to be processed first. And at any time, there must be finitely many non-blank symbols on the tape. And formally, we can describe this structure using this, where sigma here is again the input alphabet, the set of symbols allowed the initial tape content, our input string, let's say. And gamma is the finite non-empty set of tape symbols. Now, this also includes the blank symbol, and blank is not typically allowed in the input symbols, but usually we assume that the set of input symbols is a subset of the overall set of symbols. S again is the set of states, and it has to be finite, it has to be non-empty. So you need to have at least one state, and the number of states should be finite. S0 is the initial state, quite similar to finite automata. And we have F and A here. A is the set of accepting states, so it has the same concept with automata earlier. And F is the state transition function, but this is a little bit more involved in the sense that it's defined from the set of states that are not accepting, as well as the symbol read on the tape, to the next state and the symbol to be written on the current cell and the direction, left or right. This is, in general, a partial function defining state transitions. And if you remember what the partial function is, it's essentially a function, but from a subset of the domain to the codomain. So for some of the possible inputs to this function, we may not have an output. And in this case, if we encounter such a situation where the outcome for a certain configuration is not defined, we will say that the Turing machine holds. And accepting states is, of course, typically a subset of the set of all states. And one more remark here, the direction usually defined as left and right, it can sometimes also include no movement. Okay, so you can move one cell towards left, one cell towards right, or you can stay put at the same location. But that formulation is not widely used. Now, what does this structure do? You have a control unit and the memory unit, that is the tape. And what happens is, intuitively, the transition function specifies the next state transited from the current state. And recall, we have an initial state. And also which symbol to overwrite the current symbol pointed by the head that indicates the position within the tape, and the next head movement. Do we shift the position towards right or towards left? As I said, you can also have no movement, but which is not a generally used movement. So you see, using the current state, the current symbol on the tape, and the next state, and the next symbol on the tape, and the direction, these five pieces of information actually characterizes the behavior of the Turing machine at each possible state. So S and S prime here in this formulation are states. S here is the current state. S prime is the next state. When you have you are in this state and the input symbol is X, you will transit to S prime, and on top of X you will write X prime, so you will modify the tape, and D signifies the direction left or right. If the partial function f is undefined for the pair Sx, right, then the Turing machine is set to halt. So the operation is ended if that is the case. If you cannot find any configuration for your next action in the definition of the Turing machine, then we say that the Turing machine halts. If the Turing machine halts in an accepting state, then the input is set to be accepted. Here's an example. This is taken from Rosen's textbook. What is the final tape when the Turing machine T, defined by the 7 5 tuples given in this list, is run on the tape shown in this figure? So this is the initial configuration. As you recall, we start from the leftmost non-blank symbol, so that is the 0 here, and S0 is the initial state. And my state here is S0 along with the input symbol 0. So I'm going to look for in my 5 tuples or coin tuples with the configuration S0 and 0. So here it is. Okay, S0, 0. It tells me that the next state will be S0, and write 0 to this location and move right. So essentially this means do not modify the tape, do not change the state, but just move one position towards right. Okay, so my state in the next slot is still S0. I did not change the symbol in this location, but I'm now looking at the next symbol. Now my state is S0 and my input symbol is 1. So I'm looking for a quintuple involving S0 and 1. And here it is. S0, 1, current state and current symbol. This says the next state will be S1, so a state change is going to happen, and the value on the tape should be 1, and therefore I'm not going to modify it because it was already 1, and move one place towards right. So you see my state has changed to S1, and I did not modify this symbol here, and I moved 1 towards right, so I'm looking at this cell now. So S1 and input symbol 0. So S1 input symbol 0 is this configuration. This says that next state will be S0 and write S0 to the cell and move right. So since this is already 0, I'm not going to modify the tape content, but change state to S0. And I'm looking at the one on towards the right. And the input configuration is state S0 and symbol 1. So I'm again using this one, S0 current state, 1 current symbol. Therefore, next state will be S1, and write a 1 means do not change and move right. So next slot, I'm going to be looking here, and I will be in state S1. So the configuration is S1 and 1. S1 and 1, I have the configuration here. Current state S1, current symbol 1, input symbol 1. So next state will be S2. Write a 0 here. So you see I'm modifying the tape now. It has become 0 now. And my state becomes S2 and move towards left. So I'm looking at this symbol now. Okay, so current state is S2, input symbol is 1, so I'm looking for S2, 1. Here it is, current state S2, input symbol 1. So write a 0 to that location, you see, it becomes a 0. And my state will be S3, okay, and move towards right. So I'm going to take this as the input. Okay, so my state is S3 and the input symbol is 0. I'm looking for a quintuple involving the current state S3 and input state 0. I'm looking at the quintuples, but I do not have such an entry, which means the partial function is undefined for this pair, S3 and 0, which means the Turing machine halts and the operation is ended. Now, we are not given whether S3 is accepting or not, so we do not really know the result of this computation, but the configuration of the tape when the machine halts is given here.